Module 6.3, Finite Element Method in Practice. In this module, we'll learn about general FEM procedures, solving Poisson equations, steps for solving finite elements such as pre-processing, solving, and post-processing, as well as going through some of the examples other than Poisson equations. So let's start with general procedures of running a finite element method calculations. By the way, this is also known as finite element analysis problems. So FEM and FEA kind of same things. So there are three main steps: pre-processing, solution, and post-processing. We learned that in the previous module as well, but we'll go here in a little bit more detail. So pre-processing is the most challenging part and will be taking us 70% of the total effort. It consists of generating a mesh, the domain, defining the function space, so the basis of the which is the basis of the variational formulation, specifying the trial and the test functions, specifying material properties, specifying boundary conditions and initial conditions for time dependent or transient problems. So that's step one, pre-processing. Solution: once you have set up the problem, solving such problem is not that difficult. So the solution is reformulate the PDE problem as a variational problem by multiplying the PDE with a test function. We'll learn about that. And then, of course, define the boundary conditions, solve the linear system, and do time integration, especially for transient or time-dependent problems. The post-processing could also be important, and it can consist of about 20% of the total effort. It consists of visualizing the results, extracting meaningful data, validating and verifying the data, and performing error analysis. So through this example, I thought we'll go through solving a Poisson equation and side by side to these three major steps. So what is a Poisson equation? So you can see equation 1, which is a Laplacian of the behavior u for x dimension given by fx for x in all the geometry domain omega. And then we also define that at ux for d omega is ud, which is the boundary value, suppose we have given. So these two equations, equation 1 and equation 2, are essential for setting up a finite element. Now, we know the governing equation, we know the boundary conditions. And here u is the unknown function, f is a pre-described function, delta is a Laplacian operator, also written as the another form you might see in other textbook and so on. Omega is a spatial domain, and del omega is a boundary on omega. So we are specifying the boundary conditions here. The Poisson problem above is an example of boundary value problem, and in 2-dimension with coordinate x and y, we can write out the Poisson equation as this partial differential equation with del 2u del x square minus del 2u del y square is a function of x and y. The unknown u is now a function of two variable x and y for the entire 2-dimensional domain omega. The Poisson equation arises in numerous physical contexts, including heat conduction, electrostatics, diffusion of substances, twisting of elastic rods, inviscid fluid flow, and waterways. And also it has implications in fluid dynamics. Now we have the partial differential equation. Now the finite element is a variational method. So what it basically means is, most specifically, it is a weighted residual method. So in other words, instead of requiring the PDE to be satisfied exactly everywhere, we are required to satisfy in a weighted sense, given the variational form. We are multiplying this del u with v, which is the test function on both sides, and v is in a space capital V, and dx denote the area and the volume in the 2D or 3D case. Now, if you remember from a calculus class, if we have a product of two operands, so you can have something called integration by parts. So you can represent or expand del u v dx integral into del u del v dx plus del u del n and vds, right? So this is typical integration by parts for products. If you are not familiar, feel free to take a look in integration by parts for calculus. And here del u del n is the, you can see is a derivative of u with a normal direction n on the boundary, and d is a measure of surface data. Now, if v is chosen such that it vanishes along the boundary, and v, that is vx for each point x on del omega, then the second term in the right hand side, which is del u del n vds, it can be equal to 0 because v is 0 at that boundary. Now, if you substitute that, then it leads directly to del u del v dx and fx v dx. So that makes the problem much simpler in a way. So with that mathematical foundation, let's discuss about more practical things such as pre-processing and generating a mesh. So real world objects are modeled to be idealized with simpler forms to omit curvatures and fillets with a mesh. The mesh divides the problem into domain into smaller elements. So you can see this is the real, on the left hand side, real world device, and you can have an idealized physical model with a different mesh, and you can have different type of mesh elements. So the idea is you define the domain, you select the element, the bar versus beam versus pipe in 1D, or triangles, quadrilaterals in 2D, tetrahedral, hexahedral, and so on in 3D. And we also define the mesh density. So we learned about that, how important the density of the mesh is in terms of the shape function in the previous module. And then it's okay if you have something like rectangle mesh or so on, but what if you have a more complicated case such as a propeller or some complex geometry, then the building geometrical mesh could be quite challenging. Luckily, software such as Phoenix or ANSYS have inbuilt mesh generator, and there are also commercial mesh generator software such as Gmesh and MeshR and so on. So as I said, we can have a real world problem represented with a physical model with meshes, and you can have 1D, 2D, or 3D mesh elements. Now, here's an example of different types of meshes. On the left-hand side, we have a square mesh, and then we have different complex geometry, and you can see different mesh geometry can be generated with tools such as Phoenix, Gmesh, and so on. I have given some hyperlinks. If you're interested to look into some of these, you can take a look. Now, we will try to generate a mesh using a software package called Phoenix. So similar to ANSYS, which some of you might have used. Phoenix is an open source finite element code, very powerful. It can be useful for various applications. And in the notebook that I'll hyperlink in the module, you will be able to install Phoenix on Google Colab, as well as run it and see how to perform generating mesh processing and so on. So we first import the model Phoenix, and when we say from Phoenix import star, it basically import anything or everything, all the functions and models from Phoenix. Now generate a mesh. So we are generating a unit square mesh. There are different type of mesh. As you can see on the right hand side, unit interval mesh, unit square mesh, rectangle mesh, unit circle mesh, unit cube mesh, box mesh, and so on. Unit interval mesh is usually used for one-dimensional case, unit square mesh, as you can see, for 2D, as well as rectangle mesh, and unit circle mesh when you have um, circular shape, or similarly for the cube. And then you can have a combination of these elements to kind of generate particular geometry. So here we are generating now a simple triangular mesh with unit square with 0 and 0, 1, dividing them into 8 by 8 squares. And the number of nodes here are 9 multiplied by 9, that is 81. And the number of triangles are 8 multiply 8 multiply 2, which is 128. Because 3, it takes three nodes to make a triangle, right? So based on that idea. Now, pre-processing defining a function space. So especially in Phoenix, you'll see this function space coming up a lot. So in the function space is a finite element, is a mathematical construct that defines the type of function and the that are used to approximate the solution. So all the things that we did in this module and previous module to define mesh and different uh, residuals, shape function, and so on can be easily built in Phoenix packages. And the role is to define basis function. So linear versus quadratic support variation formulations. So the weak form of governing equation is formulated within function space. It ensures the compatibility, so ensure the trial and the test function are compatible with the problem's boundary conditions. And there are different types of function space. Scalar function space, such as the temperature and pressure. In Phoenix, we will denote is equals to V, which is the space is function space mesh. So you'll give a mesh. This could be a square mesh, rectangle mesh, P and 1 for linear elements, vector space such as displacement and velocity, and tensor space such as stress. Now we are defining still the function space. So we define a finite element function space. The argument, second argument P specify the type of element. The type of element here is P, implying standard Lagrange family of elements. You may choose a Lagrange or continuous Galerkin to specify the type of element. The argument can also be discrete Galerkin for discontinuous Galerkin methods. And the third argument specify the degree of the function. Here the function are piecewise linear, hence 1. And there could be a rectangle mesh and so on, and quadrilateral mesh in 2D, 3D, and so on. Now we also need to specify the trial function. So trial functions are defined within a function space and used to transform differential equation into weak form. So remember we did the integration by parts. That's how we kind of represent a strong or PDE function into a weak form. So the trial and test function are fundamental components in variational formulation of FEM. So trial function represent the approximate solution to the problem, and that which is the U, and the test function V is used to weight the residual of the differential equation on the weak formulation. Both trial and test function are elements of the same function space. And in some cases, the test functions are chosen to be orthogonal to each other for simplicity in solving the algebraic equation. Luckily, all of these are already performed in software such as Phoenix or ANSYS. And it must satisfy the continuity and differentiability requirement of the problem, because we do want to get the differentials. And you can also have several mixed formulations, but we will not go too much detail into that. We also need to specify material properties. It could be Young's modulus, Poisson ratio, density, thermal conductivities. For elasticity, we might need to specify elastic constants such as Young's modulus, Poisson ratio. But for this Poisson equation solution, we do not need it because we have assumed the material property to be 1, for example. We also need to define the variational problem. And for defining the variational problem, we have to know something called UFL, unified form language, right? And then it can be the basic algebra-based notation such as plus, minus, multiplication, and so on, or power given by 2 star, or division given by the slash, or it can be functions such as exponential, natural logs, ln, sine, cosine, product functions such as a dot product of a and b, inner product, outer product, tensor algebra such as trace, determinant, inverse, and so on, differential operators such as the divergence, and the gradient, curl, rotation, and so on. And this, of course, not the complete list. There are certain usual notations. So A is left hand side of a partial differential equation. Capital L is the right hand side, and so on. These are some well-defined notations in this setup. So we need to specify the variational problem. And in Phoenix, the variational problem is specified by translating the mathematical expression of integrand into unified form language that we talked about, which is a domain-specific language based on Python and C++ syntax. So A, which is the left hand side, is dot of two entities, grad u and grad v. So gradient of u and gradient of v. Remember, u is the trial and v is a test function necessary for the weak formulation. And f is assumed to be constant minus 6. It can be a function as well. So now the equation can be rewritten as L, right hand side, equals f v and dx. And here a is the integrand on the left hand side, L is the integrand on the right hand side, dx denotes the measure. Since constant minus 6 define a constant expression, another way to write is f equals to expression like this. The UFL is an integral part of Phoenix library and also on other libraries as well. We also need to specify boundary conditions. So for the Poisson equation, do not have a unique solution without proper boundary condition. Next, we need to specify the boundary conditions at u, at ud. D is the boundary there on the del omega. We need to define an expression of ud. So this can be 1 plus x square plus 2y square for a rectangle or a square mesh. And it can be anything else. It can be constant value as well, or it can be derivative for Newman condition. The UFL specifically uses a character string containing an expression of C++ syntax. So here we define the boundary condition as 1 plus x0, which is x0 is x square, and 2x1, which is the basically the y square. So we set the degree to be 2 because UD may represent the exact quadratic solution instead of linear solution for our test problem. We also need to define an integrator to determine whether a point is on the Dirichlet boundary and specify the boundary condition. So here we define the boundary as a Python function. So Dirichlet boundary condition given here. And input on boundary specify whether a node is on physical boundary. We'll show how to define more complicated boundary conditions in later examples, but here we'll be showing, like you can see, the function def left x on boundary near x0 is 0. So it's just specifying that boundary condition. Now, once this is set up, which is quite challenging, once it is set up, you can solve this with a very simple command: solve a equals L for unknown variable u. Or you can also provide boundary conditions, BCs, or have more sophisticated parameters in terms of what kind of solver you want to use, what kind of optimizers you want to use, and so on. Post-processing, so after the solution of u, which is unknown, a PD is computed, we occasionally want to compute functional of u, such as this del u modulus square, so which often reflects some sort of energy quantity. And another frequently occurring function is the error. So UE is the exact solution and U is our finite element solution. And you may want to calculate the error. We will learn about that in one of the examples. The error is of particular interest when studying convergence properties of finite element method. So you can have linear element, quadrilateral element, 5 shape function versus 500 shape function, and see how does the error look like. That is where convergence is important. We did some sort of convergence studies in DFT also, if you remember. So it's kind of similar idea where we have multiple degree of freedom of parameters of a model that we want to converge to a certain extent. So now we can do post-processing using a function in Phoenix called plot. So u is unknown, and we are plotting here how the u, the unknown, varies across the domain here. We can also calculate errors using the error norm in the Phoenix, and you can see the errors are very minimal. So basically the UD, the boundary condition on the value of the unknown at the boundary conditions are very similar to that of what we Phoenix or finite element predict as given by the scatter line. So if you have a complete agreement, it should be complete x equals to y, or a y equals to x straight line with 45-degree angles and everything lying on it. If it's not a good fit, there will be deviations. That's one of the way to see it. Now, let's talk about some inherent errors. So we talked about in the previous module and slides is we are trying to simplify the geometry. So we can take the domain and approximate the domain, but You might have a true deformation as given in the left, and when you try to model with finite element with linear element, it may not be suitable, as you can see, or even with quadratic element, then you might need to have something like cubic element. And this, uh, even after that, you will have to do integration with something like cosine quadrature, and that also can add another level of error in finite elements. So that's why it's important to select what kind of optimizers, what kind of shape functions, what kind of elements, and so on, what you are using in finite element solution. Some of the common mistakes by users, so elements are of wrong type. For example, cell elements are used where solid elements are needed. This is a very common problem. What kind of elements to select? There could be distorted elements. Supports are insufficient to prevent all rigid body motions. Some of the supports, such as the boundary value problem, again, can be insufficient. Inconsistent unit. So unit is a major issue. So make sure that always your units are consistent on the left hand side and right hand side. And of course, you do not want to give too large values for the stiffness matrix or K that can lead to numerical difficulties. So always good to normalize with something. So although we talked briefly about solving Poisson equation, in the notebook that I'll provide, I've given several examples how to generate different type of meshes, how to solve 2D linear elasticity problem, orthotropic linear elasticity problem, asymmetric formulation of elastic structure of revolution, heat equation for thermal properties, and thermal elastic evolution problems. Luckily, Phoenix provides several other examples, and I'm sure other softwares also provide several other examples, but the basic idea is going to be the same.